All right, welcome to The Explainer. Ever just stopped and wondered how a simple idea, something in your head, turns into actual moving pixels on your screen? Well, that's exactly what we're going to do today. We're taking a deep dive from human thought all the way down to machine action.
So how does a simple line of code, something a person writes, become this complex action you see? I mean, it's a huge question, right? It's really the heart of all modern tech. Today, we're going to peel back all those layers and see how the magic actually works.
All right, so let's get into it. The best way to think about this whole process is like a tower of translation. We start at the very top with language that we humans get, and we work our way down layer by layer until we get to the raw logic that the machine itself can actually run.
So, you can see it's basically 4 levels. At the very top, you've got just a plain old idea in a natural language, like English. I want the character to jump. Then a programmer takes that and writes it in a high-level language, something like Python. But the computer doesn't get that either. So that gets translated down another level to assembly language. Now we're getting warmer. This is much closer to what the hardware understands. And then finally, at the very bottom, you have machine language. We're talking pure ones and zeros. That's it. That's the only thing the computer truly understands.
So what's the difference between these two? Well, it's really a classic trade-off. On one hand, you've got high-level languages. They're amazing because they're portable. You can write the code once, and it'll run on all sorts of different computers. They hide all the messy, complicated details. But then you have assembly. Assembly's the opposite. It's totally specific to one type of computer hardware. You lose that convenience, but what you gain is just raw power. You get direct, hands-on control of the hardware itself. Okay, so let's jump all the way down to the bottom of that tower. We're at the foundation now. This is where we find the machine's native tongue, what it's actually speaking.
And this is it. Machine code. Just a long stream of ones and zeros. These are called opcodes, which is short for operation codes. And I mean everything. Adding 2 numbers, changing a color on your screen, playing a sound, it all boils down to a sequence just like this one.
Yeah, kind of hard to read, isn't it? For us humans, trying to make sense of endless strings of ones and zeros is, well, it's basically impossible. And it's super easy to make a mistake. Our brains just don't work that way.
Right. And that's exactly why we came up with a better way, a kind of shorthand to make our lives easier. And that shorthand is called hexadecimal.
And the way it works is actually pretty brilliant. You just take the binary string and break it up into little groups of 4. And every single group of 4 bits corresponds to exactly 1 hexadecimal character. So you go from 0 all the way up to F, which, as you can see, stands for the binary 1111.
And check this out. This is a perfect example of what I mean. To a computer, the word wooden means absolutely nothing. It doesn't see letters. It just sees a sequence of numbers. In this case, those are the ASCII codes for each letter, represented in hex. That's what the machine can actually work with. Okay, so now we get the language, right? We know how we talk to the machine. But where does all this work actually happen? Well, for that, we need to go inside the silicon brain of the computer, the CPU. Think of it as the main workshop. And inside this workshop, you've got a few key players. First, there's the control unit. That's like the foreman or the manager, telling everyone what to do and when. Then you've got the arithmetic/logic unit, or ALU. That's your master craftsman, the one doing all the heavy lifting, all the math and the logic. Data gets stored temporarily on a little high-speed scratch pad called registers. And all these parts talk to each other using buses, which are basically the superhighways for data.
Now these registers are so important for speed. Imagine you're a chef. Registers are like that tiny bowl of salt you keep right next to the stove. It's the ingredients you need right now. Because they're physically on the CPU chip itself. They are the absolute fastest memory in the entire computer. No waiting around.
And the ALU, well, that's the real number cruncher. This is the part of the CPU that actually does the math, the addition, the subtraction, and the logical stuff like checking if one number is bigger than another. It's the powerhouse, the engine of the whole operation.
Okay, now this is really cool. Look at how these registers are designed. Take this one, EAX. It's a 32-bit register, right? But you don't have to use all 32 bits at once. It's designed so you can access smaller pieces of it. You can grab just the lower 16 bits, which is called AX, or you can get even smaller and grab just an 8-bit chunk, like AH or AL. It's this incredibly clever design that gives programmers a ton of flexibility.
So let's put it all together. We've got the language and we've got the workshop. So what happens when an instruction actually shows up for work?
Let's follow one on its grand tour and see this fundamental rhythm of computation in action.
It all comes down to the simple three-step dance, and it happens over and over and over again. First, the control unit has to fetch the next instruction from memory. Then it has to decode that instruction, figure out, okay, what am I being asked to do? And finally, it passes the job over to the ALU to execute the command. Fetch, decode, execute. That's the heartbeat of the computer. And it's a heartbeat that pulses billions of times every single second. It's just mind-boggling.
And that quote on the screen really nails it. When you get right down to it, what we call a program or software is really just a list of instructions. It's a to-do list for the CPU, sitting there in memory, where every single item on the list has its own specific address, just waiting for its turn to be fetched, decoded, and executed.
Okay, so you might be sitting there thinking, this is cool, but we have Python and JavaScript now. Why do I need to care about any of this low-level stuff? And that's a fair question, but the answer is, it matters a lot.
Because knowing what's happening under the hood, it's like having a superpower. If you understand the hardware, you can write code that is insanely fast and efficient. When things go wrong, you can use powerful debugging tools to see exactly what the CPU is thinking, looking at the registers and memory directly. You can even reverse engineer programs to figure out how they work without the source code, and for some jobs, like making video games or programming a robot, this knowledge isn't just a bonus, it's absolutely essential.
Look, at the end of the day, it's not about forcing everyone to write assembly. It's about something bigger. It's about building a real gut feeling, an intuition for how computers actually work. And when you have that foundation, you become a better problem solver no matter what you're working on at any level.
Suddenly, the computer isn't some mysterious black box anymore. It's a tool, an incredibly powerful one that you actually understand. And I promise you, once you've seen what's going on under the hood, you'll never look at your screen the same way again. It changes your whole perspective. So the real question is, now that you have a glimpse of how the machine truly thinks, what are you going to build?